Good morning to one and all. My name is Dr. G.V. Rao, Professor in the Department of Civil Engineering, Vijnan Institute of Information Technology, Duvada, Visakhapatnam. Today we are going to discuss about fluid properties. What is fluid? What are the fluid properties? Right? Fluid is a substance which flows continuously when subjected to shear force. And fluids are basically classified as two ways. One is liquids, another one is gases. Liquids example water, the example of gases is air. Now we are going to discuss about fluid properties. These are the fluid properties. Density or mass density, weight density or specific weight, specific volume, specific gravity, viscosity, kinematic viscosity, surface tension, capillarity and compressibility. These are the basic fluid properties. Now we are going to discuss about one by one. First fluid property, density or mass density. Density is defined as the ratio of mass per unit volume. Ratio of mass per unit volume. Therefore, it is denoted by symbol rho. Mass density is denoted by symbol rho. Mass density is defined as the ratio of mass per unit volume. Therefore, mass density equal to mass per volume. Therefore, mass units kg in SI system, volume units so meter cube in SI system. Therefore, mass density units are kg per meter cube in SI system. Right? The density of liquid may be constant, but the density of gases changes with the variation of temperature and pressure. Here, the density of liquids may be constant, but the density of the gases are varies with respect to the pressure and temperature. Here, the density or mass density equal to mass by volume. In case of liquids, any change of temperature or any change of pressure, the volume change is very small. Therefore, density is equal to mass by volume. There is no change in the volume because of the changes of temperature and pressure. Therefore, mass density almost all equal to constant in case of liquids. Okay. Whereas in case of gases, the mass density changes from or changes with respect to temperature and pressure. Same formula, density equal to mass by volume. Mass is constant because of temperature and pressure. The volume changes. If the volume decreases, density increases. If the volume increases, density decreases. Volume decreases, density increases. Volume decreases, density increases. Volume increases, density decreases. So, if any change of volume because of the temperature changes and pressure changes, automatically the volume of the air or volume of the gases are having abnormal changes. Therefore, the mass density also changes with respect to the temperature and pressure. Right. Mathematical form, rho mass density is equal to mass by volume. Here the mass density value is having some standard values. For water or standard liquid, mass density rho equal to 1000 kg per meter cube. This is very important value. The mass density of water or the mass density of standard liquid is 1000 kg per meter cube. Similarly, mass density of mercury. Mercury is the heavy liquid that is having high specific weight, that is having high specific gravity. Therefore, The density of the mercury is mass density of mercury is equal to 13,600 kg per metric cube, and mass density of glycerin, that is equal to 1260 kg per metric cube, and mass density of air is equal to 800 kg per metric cube. The mass density of air is less than the mass density of water, right? These are the standard values for the air, water, glycerin and mercury, right? The density of water is 1000 kg per metric cube. We can say it is 1 gram per cc. The density of mercury 1000 kg per metric cube. This is also known as 1 gram per centimeter cube. The density of water 1000 kg per metric cube. This is also known as 1 gram per centimeter cube. Rho is equal to 1000 kg per metric cube. This is also known as 1 gram per centimeter cube, right? Next, weight density or specific weight. Weight density means it is defined as the weight to unit volume. Weight density or specific weight is defined as the weight per unit volume. That means it is denoted by small w. Weight density is denoted by small w. This is equal to weight per unit volume. Therefore, weight units in an SI system, newtons, divided by volume units in SI system, metric cube. Therefore, the units of weight density or specific weight is Newton per metric cube, right? Not mass density, weight density. This is weight density. Units of weight density is Newton per metric cube. Mathematical equation for the weight density or specific weight, weight by volume, that are Newton per metric cube, is the units of weight density or specific weight. Now we are going to develop the one relation between the density and specific weight. Density and specific weight. We know one standard formula, weight density equal to weight density or specific weight is equal to weight per volume. Weight is also nothing but mass of fluid and acceleration due to gravity divided by volume, right? So mass of fluid divided by volume is also nothing but what? That is mass density. Therefore, unit weight equal to mass density into acceleration due to gravity. Unit weight or specific weight or weight density equal to mass density into acceleration due to gravity. The units of weight density is equal to Newton per metric cube, and the value of weight density is equal to, this is very very important value where we are going to solve the problem, 9810 Newton per metric cube. Weight density is equal to 9810 Newton per metric cube, right? This is the relation between the weight density and density. Here one more point, weight density equal to rho into g. Rho is the mass density, g is the acceleration due to gravity. But here weight density depends on rho and g, but the density depends on temperature and pressure. If the temperature increases, volume increases, automatically density reduces. So depends upon the temperature and pressure variations, automatically what is the formula for the density? Rho is equal to mass by volume. If the volume changes with respect to temperature and pressure, therefore the mass density depends on temperature and pressure, but the weight density depends on the mass density. Therefore weight density is function of temperature and pressure, right? This is about specific weight or unit weight or weight density, right? Specific volume is defined as the ratio of volume of fluid to its mass of fluid. That means specific volume equal to volume of fluid to the mass of fluid. What is the volume of fluid to the mass of fluid represents? This is the reciprocal of mass density. Mass density is equal to mass by volume, but specific volume is nothing but volume by mass. Therefore, this is equal to 1 by rho. Rho equal to mass by volume. But here specific volume is equal to weight by volume. Weight by volume is also nothing but 1 by rho, because rho is equal to mass by volume. Right? This is the relation between the specific volume and the density or mass density. Volume is equal to weight by volume. This is also nothing but 1 by rho. The specific volume is reciprocal of the mass density. Right? Right. Specific gravity. Specific gravity is defined as the ratio of weight density or density of the fluid to the weight density or density of the standard liquid or standard fluid. Right? We know that standard fluid is taken as water. Generally, the standard fluid is taken as water. The water density is equal to 1000 kg per meter cube. The water weight density is equal to 9810 Newton per meter cube. Right? These two are the standard values for the density and mass density. Right? The specific gravity is called the relative density. Specific gravity is also nothing but relative density. Okay. Specific gravity is denoted by S. Specific gravity equal to density, weight density to the weight density of standard liquid, or specific gravity is equal to mass density to the mass density of standard liquid. Specific gravity is defined as the weight density or density of the flowing liquid or of the fluid to the weight density or density of the liquid. Here, for example, this is one liquid. Weight density of any liquid, specific gravity equal to weight density of any liquid divided by weight density of the standard liquid. And also specific gravity equal to mass density of liquid divided by mass density of the standard liquid. Right? Standard liquid means, here we are going to take the standard liquid is water. Water is the standard liquid. In case of water, mass density equal to 1000 kg per meter cube, whereas in case of water, the weight density, in case of water, weight density or unit weight equal to 9810 Newton per meter cube. This is the standard liquid density and weight density. Right? Okay. This specific gravity is also known as relative density. This is denoted by the symbol S. Right? And this is dimensionless because the upper unit and lower units get cancelled, because this is the ratio between the weight to weight or density to density. Mathematical form of specific gravity equal to, already I have given weight density of the liquid to the weight density of the water, or density of the liquid to the density of the water. Okay. And specific gravity for gases, weight density of the gases to the weight density of the air. Okay. Right. Last one, weight density of liquid S is equal, this is one more relation from this one. From this equation, weight density of liquid, weight density of liquid is equal to specific gravity into weight density of standard liquid. Weight density of standard liquid, that is equal to specific gravity of the liquid that is given in the problem. Weight density of the standard liquid is equal to 9810. This is the weight density of the given liquid. Like that, mass density of the liquid is equal to density of the liquid is equal to specific gravity of the liquid into density of the standard liquid. Density of the standard liquid. This is equal to S, that is the density of the liquid given in the problem. If they have given the mass density of the water, okay, otherwise we are going to take 1000 kg per metric cube, 1000 kg per metric cube, right? First we are going to discuss about definition of viscosity. Viscosity is the property of fluid which offers resistance to the movement of one layer of fluid over the another adjacent layer of the fluid. Right here, this is the boundary. The velocity over the boundary is 0. Y is equal to 0. Velocity of flow over the boundary U is equal to 0. Gradually from the boundary, normal to the boundary, the velocity gradually increases, right? When two layers of fluid, here this is one layer of fluid, the velocity is u. This is another layer of fluid, the velocity is u plus du, right? The one layer of fluid velocity u, the another layer of fluid velocity u plus du. The two layers are provided at a distance dy, apart at a distance dy. So here, because of this change of velocity, here velocity is u, here velocity is u plus du, that means velocity increases. Here the velocity, some velocity, 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 velocity. From starting point onwards, from the boundary, the velocity gradually increases. We have taken two layers, this is the layer 1 and layer 2. These two layers are dy distance apart. The velocity at the layer is equal to u, the velocity at this layer is equal to u plus du. The change of velocity from one layer to another layer, here develop the velocity gradient, that is du by dy. The velocity gradient exists because the velocity changes from one layer to another layer. The viscosity together with the relative velocity causes a shear stress acting between two fluid layers. Acting between the fluid layers. This is one fluid layer, this is the another fluid layer. Between these two fluid layers, viscosity produces. Viscosity is denoted by tau. Now, this is one fluid layer, this is the another fluid layer. Here, the top layer causes a shear stress on the adjacent lower layer. Suppose this is one fluid layer. This fluid layer causes a shear stress on the adjacent lower layer. This is the lower layer. And the lower layer causes a shear stress on the adjacent fluid layer, that is the top layer. Okay. The top layer causes a shear stress on the adjacent lower layer, while the lower layer causes a shear stress on the adjacent top layer. The one layer over the another layer develops a shear stress. Here, the shear stress, automatically the shear stress is developed between these two layers. The shear stress is directly proportional to velocity gradient, that is equal to du by dy. Right? The shear stress is directly proportional to du by dy. Now, the shear stress is equal to mu into du by dy. Here mu is the constant of proportionality. This is also known as dynamic viscosity or viscosity of the fluid. Right? Tau is equal to mu into du by dy. This is the relation between the shear stress and velocity gradient, and also relation between the shear stress, viscosity and velocity gradient. Right? The shear stress is directly proportional to the rate of change of velocity with respect to y. Right? This is the variation of velocity. This is the y direction. It is denoted by tau. Therefore, shear stress tau is directly proportional to du by dy. Therefore, tau is equal to mu into du by dy, where mu is the constant of proportionality or viscosity or dynamic viscosity. This du by dy is also known as rate of shear strain, rate of shear deformation, and also known as velocity gradient. Mu is the viscosity of the fluid. Tau is the shear stress. Right. Now we are going to derive the units of viscosity. We know one relation between the shear stress and viscosity and velocity gradient, that the relation is tau is equal to mu into du by dy. From this equation, we are going to develop the units of viscosity. Now, viscosity is equal to tau into dy is equal to mu into du. Okay, right. Therefore, mu is equal to tau into dy divided by du. Right, this is equal to, this is tau is nothing but force by area. Tau is nothing but force by area into du is nothing but change in depth du is nothing but change in velocity, right. Therefore, this is equal to units of viscosity. Force is represented by Newton divided by area, that is meter square, into change in depth, that is also mentioned by meters, divided by change in velocity, that is equal to meter per second, right. This is equal to Newton, right. Now, force Newtons, area meter square into change in depth meters divided by change in velocity meter per second. This is equal to Newton per meter square into meters into second per meter. Now, meter gets cancelled. This is equal to Newton second per meter square. The units of viscosity is Newton second per meter square, and also sometimes Newton per meter square is also nothing but Pascal. PA, Newton per meter square, is also nothing but Pascal. Therefore, this is known as Pascal. Therefore, units of viscosity equal to Newton per meter square into second. This is equal to Pascal second. Units of viscosity is Newton second per meter square or Newton per meter square into second. Newton per meter square, in place of Newton per meter square, we are going to take the Pascal. Pascal second is also units of viscosity in SI system, right. MKS units of viscosity, kg force second per meter square, CGS units of viscosity, dyne second per centimeter square. This is also equal to 1 poise, right. 1 poise equal to 1 by 10 Newton second per meter square. This is very important relation where we are going to solve the problems. 1 poise equal to 1 by 10 Newton second per meter square, right. Kinematic viscosity means is the ratio between the viscosity to the density, right. Viscosity of fluid to the density of the fluid. Mathematically, kinematic viscosity nu equal to viscosity divided by density, that is equal to mu by rho, right. Where nu is the kinematic viscosity, mu is the dynamic viscosity of the fluid, and rho is the density of the fluid. Kinematic viscosity of the fluid, density of the fluid. Now, units of kinematic viscosity is meter square per second. Now, we are going to derive the units for the kinematic viscosity. Here, kinematic viscosity equal to viscosity divided by density. Viscosity units Newton second per meter square divided by density. Density is nothing but kg per meter cube, right. This is equal to Newton second per meter square into meter cube divided by kg, right. Now, Newton is nothing but, force is nothing but mass into acceleration due to gravity. Newton is the units of force. Force is nothing but mass into acceleration due to gravity, that is equal to mass into acceleration due to gravity g into s divided by meter square into meter cube divided by kg. Mass units kg into g is acceleration due to gravity, that is equal to meters per second square into s into meter cube divided by kg. Kg gets cancelled, square seconds cancel. Right here mass into g divided by this one. Right, this is equal to mass units kg into acceleration due to gravity, that is equal to meters per second square into s divided by meter square into meter cube divided by kg. Kg gets cancelled, meter square, this is a cube, square cancel, only m here, 1 m here, square and s cancel. Therefore, units of kinematic viscosity equal to meter square per second. Units of kinematic viscosity equal to meter square per second. Right? Units of kinematic viscosity is equal to meter square per second, that is in SA system. And units of kinematic viscosity in CGS system is equal to 1 Stokes. That is in CGS system. And also the relation between the CGS units and SI units, 1 Stokes equal to 10⁻⁻⁴ meter square per second. This is very important relation where we are going to solve the problems. 1 Stokes equal to 10⁻⁻⁴ meter square per second. Right? Thank you one and all for listening my class.